Yeah, no kinds of questions, I think. Yeah, yeah, so they have one, yeah, one dolphin. So, all going on the tours?
Yeah.
Right.
Yeah, so we're all downstairs wearing our coats with them all.
Right. Well, at least we've got some people definitely turning up. So,
well, we've got 3 speakers. I think, to be honest, it's a win.
yeah. Okay. So,
We have a big poster. I can take it away here.
so I've asked Faye Rand, who was the other person up with the poster, then went quiet on that was so yeah.
Yeah.
All right. Jacob, what was that special shortcut for like changing windows and Teams that you had? Alt tab. Aha.
That's kind of all the time. So
It's here, Fred, it's here, it's this one. Yeah, it was a bit flaky, to be honest.
Okay. There are some better ones. So, I should also think that port is normally worth it. Take that.
Okay.
I don't know
Well,
if
let's
it's
do that. Let's do that because that one down there. I think
It's just the ones for those who can go and have a look.
yeah.
Sorry. Didn't go into the hole. Okay.
to go.
Yeah. Yeah, that sounds like it's. Oh, okay.
It's long moving, it's not too bad.
Yeah. Yeah, don't check the video. Oh, yeah. Okay.
Oh, that will probably stop early. I don't even know.
It's okay.
That's your, it's like video.
Yeah. Also, we may have to stop the car.
Are there any other potentially different sides?
No. All that there, it's just at the end, so I think it's slightly to.
Yeah.
Actually, do you know what? I was shocked to realise that we never had these more cars. I was not expecting them. I was global whole production. I was generally expecting to see going to UK is going down. But well, we can never produce more cars. India really pushing it. So yeah, I was pretty surprised actually.
Yeah, no, in terms of digging that, yeah.
Yeah.
Yeah, and it's if you look at like the was it the the whole institute for the world. I mean, it's fascinating. It's just,
Yeah, you can get the impression, I really got the impression of all you poets were imagine those vibes, not the general vibes, which is a better thing. And then smell the same oil.
yeah. It's a story.
Yeah, yeah.
Now, it's really introducing you, it's going to be something like that teacher in the balance. I think you can introduce something like that. Yes. Okay, so it's not really.
I'll tell you how to.
Yeah, so so basically something about so I can stand up very much of a new welcome. And this is the first of the whole series of lectures that are going to say like the 110 minutes. All the roles that you want to know about more detail. Each lecture has a theme. So you know anything like that to change the transition. Yeah, yeah. Each lecture has a theme. So two stuff running in parallel with all of this. We're very excited to a really nice students partners that are in school actually seeing an experience of amazing research and teaching and learning. From a health and safety perspective, it should be a lot of science. This is your access. Sharing other people and then, right, first up, we have Professor Matt Jackson, with those dialects.
Then in terms of bringing my understanding, I was a bit
Yeah, so if they come to you get that, so you get the speed. You might kind of get the some other things like yours. And then I'll really this.
So I didn't do that.
Yeah, so what we can do basically, so yeah, so if we go below what we did on the other and so that once we do that, do you want to I think we just what we can do then is we get the things of the months, and then what things do in time. So basically, we've got these actually 620 and that's going to be the whole plan. So that's a thing like 7 by 6 so with this, then you really like I mean, I'll just pick a chance of it might say Yeah.
And now, and to them, to be working in sort of.
And then if you want sections, I think it's so they're going into the with minds as sports that was she went to years ago. I think that's that's online as well. So I'll work on my series, yes, just to keep happen. So
I log in as well to social, so yeah, like it's better I still got so much. We do specialising. When you go to one, I'll be like putting on pound special sitting on it's a bit of then I
yeah, what you could always do is if you say that you like that, you can always be there so you can reach your actor. I think you know to where the both part of it. Yes, the other on makes sense. But that means like really can't keep an eye on what's going on there. And they keep them for something, yeah, my with the
They're all green and they're all saying 100%, so it should be okay.
so I think when you do that stuff is obviously and then with the black going. If you give your life to maps.
Yeah.
I hold on to it because I can think whilst we're getting on sorted.
Like nothing that's short on it. You're gonna need to do that on my own, make sure I'm there.
Yeah.
What's the time? What is saying that? Oh, yeah. Yeah. Obviously, yeah. It's like, I just so I'm not sure.
Yeah, I know. I know.
She's sitting over there. Just one bar, that's no more. Which kind of, this is the one he said.
It's like two. This is unbelievable.
But then the next part.
Yeah.
Yes, I did something on. I didn't feel like that. At no point, I get all of them, but it's, I don't know what to do.
Let's take it down a little bit. Let's get to previous one.
And then we're going to go round and some
So you're going to be the roving one. Capturing everything we've been like babbling about. So that's fine. We'll just cut that out at the end. Okay. So yeah, you're gonna start with the fire.
do off my fire.
Sounds good.
Good evening, everybody, and welcome to the Department for Earth Science and Engineering, which is one of the two departments in the Royal School of Mines here at Imperial College London. My name is Dr. Sarah Gordon. I'm a professor of practice here in Earth Science and Engineering, and my partner in crime is...
I am Fred Richards. I'm an assistant professor in Earth Sciences.
So for those of you who are here in this room, firstly, a massive thanks to those of you who have shunned the tube strike. As you will see, we have obviously scheduled our lectures ahead of all the tube strikes that are happening over the next few months, and they have copied us. So we are considering moving the lectures. We're not sure yet, but you never know. It might go down really well tonight because we've got nowhere else to be. So you can all stick around for the networking after we finish our fantastic talks that we've got this evening. For those of you who are in the room, we're not expecting any fire alarms, but if those dulcet tones do happen, can anybody remember where to go? I got silence, by the way. For those of you who are listening online, there were some very odd looks in the room. Yeah, okay, we go out the fire exit here and you get spat out into that main quad area beside the big blue building. So we will look after you if there is a fire alarm. If there isn't a fire alarm, then you will see that we do have posters back in G35 that you all walked past earlier on. We also have some drinks and some refreshments for networking after we finish this evening. So this is the first of a series of lectures that we have, and we put these together to celebrate the 175th anniversary of the Royal School of Mines.
So yeah, so what we're hoping to get is amalgamation of all the people who currently work here, but also trying to get our alumni back in through the door, and also interested members of the public to get engaged with what we're doing here at the RSM, to be inspired by what we're doing, and also to help us think about what the next 175 years of the RSM might look like.
Each lecture or series of lectures is set up to have a slightly more senior member of staff. Matt is giving me a very strange look at the moment. No, I said a more senior member of staff, not necessarily old. Age has nothing to do with it. We also have an alumni, so somebody who has studied within the department and also someone who is earlier on in their career as well. And this is really to try and let us explore not only some of the variety of different types of research that we do within each theme, but also how we teach them and how do we try and inspire everybody else coming through the department to actually push things like the energy transition onto whatever might come over the next 175 years. So this evening, we are really, really delighted to have three awesome speakers. They've each been given a very strict time slot. Some of them have about 1 million slides, so we will see how quickly they speak. But our aim is to allow each of them to give a bit of a sort of TED-style talk. There may then be time for questions, both from within the room, but also online as well. And then at the end, we're going to bring them all up onto the stage for a bit of a panel session. Heckling is very much welcome, as are all questions. Nothing is banned in this room, but of course, please do be respectful of our fantastic speakers who have taken the time to come and speak with us here today. Fred, is there anything else?
So I think we can take it away.
Excellent. So with that, whilst we welcome the fantastic Professor Matt Jackson to the stage for our first talk of this evening. Matt is our chair in geological fluid dynamics, and he's going to tell us exactly what that means. And I believe in true geological style, he does also have hand specimens. So he's going to start off with a rock. Matt, over to yourself.
Thank you very much.
Give him a round of applause, everyone.
Okay, good evening, everyone. I do need some audience participation this evening. So at the right moment, and you'll know when that moment is, I need you to either shout coal, oil, or Cornwall. Okay? Are you ready for that? And those of you online are also very welcome to participate, but we won't be able to hear you in the room. But please do shout that out at home. Okay, so I want to start off today by just setting the scene. You know, what is the energy transition and why do we need it? And then say a little bit about what we're doing here at Imperial at the Royal School of Mines to address that. So I do indeed have a hand specimen. I have in my hand a shiny black rock, a major fossil fuel source, which is, I knew you would know when to do it. So let's look at a little bit of history. This is, we're going to see a few of these kinds of graphs, so I'm going to just talk you through it. This is a plot of UK annual coal production through time. And coal production here is not measured in terms of tons, it's measured in terms of the energy it could deliver. And that allows us to then compare across different types of fuel source. And you can see that we were producing a lot of coal through the early part of the 1900s. In fact, coal was the dominant energy source for the UK for about a century, supplanting, in fact, renewable sources like wind mills and water mills to become the major energy source until we started to see this decline. And in fact, now we produce no coal at all in the UK. And as you would expect, the Royal School of Mines, there was a major area of research that was focusing on how we could optimally produce coal and the challenges to producing coal, not just with a UK focus, but also internationally. We do a lot of very internationally focused research here. But coal went from being king to being supplanted itself in turn by another major fossil fuel source. So I have in this vial here a black sticky liquid, which is, yes, you see, you're really good, right? So you're all over this. So we can look now at a plot of oil production in the UK as a function of time, which really kicked off in the 1970s and peaked. And in fact, now we are also in a decline stage of oil production in the UK as we exhaust the resources of the North Sea. And oil production was also a major focus of research and teaching in the Royal School of Mines for many years, both with a UK and an international focus. So now I tend to think personally of coal with our UK focus as a rather kind of outdated fuel now, but actually if we look globally at coal production, in fact, we have never produced more coal than we do at the moment. And although the UK's production of oil might be declining, if we look at global oil production, we've also never produced more oil. And that's a problem, okay? Because these fossil fuel sources are full of carbon. So when we burn them to make energy, that carbon is released as carbon dioxide and it enters our atmosphere. So we can look at the content of CO2 in the Earth's atmosphere over time. We can look back, in fact, over several hundreds of thousands of years of Earth history, and we can see that, you know, the content of CO2 is relatively stable. It oscillates, but it fluctuates from somewhere between 200 and 250 parts per million. And then we see at the right-hand end of this graph, this strange vertical line, which looks a bit like I've made a mistake somehow in plotting the data. So what we can do then is to zoom in on the much more recent history of the Earth. So now we're looking back over the last 2,000 years, and you can see this relatively stable CO2 content. Then we suddenly see this very, very rapid increase, now approaching or exceeding, in fact, 400 parts per million. And in fact, this upturn in CO2 production starts at around 1850. The Royal School of Mines, or indeed its forerunner, was founded in 1851. Now, I'm not saying that the research we did in coal and oil production was the cause of this. Of course, in fact, the timing is coincidental because the Royal School of Mines was founded as part of that huge increase in interest and engagement with science, technology, and innovation that came alongside the Industrial Revolution, where we started to burn lots of coal. But we know that CO2 is a potent greenhouse gas. This increase in CO2 in our atmosphere is causing the planet to warm significantly, and that is going to have a significant impact on our climate and how we live on the planet. So the energy transition is really around eliminating the combustion of fossil fuels to produce energy, and where that's unavoidable, to capture the CO2 that's emitted and either store that safely or to find other uses for it. And the energy transition affects energy in all the ways that we use it. It affects electricity generation, it affects transport, heating, and heavy industry. And it also offers, and we see this right now in the current geopolitical context, advantages beyond CO2 emissions reductions. Generally speaking, when we produce renewable energy, we do it locally. That means that we significantly reduce our dependence on supply chains that are at risk of geopolitical uncertainty. And also, if we do this right, if we do the energy transition right, we can also guarantee equitable and fair access to energy and eliminate or at least significantly reduce fuel poverty. So that will be the ambition for the energy transition and our contribution to it. And the news is good in many ways. And so if we look at the increasing contribution of renewable energy generation in the UK context, we can see a really significant increase over the last 15 years, particularly driven by the growth in wind generation. And we see that increase in renewable contribution also if we look globally. Big contribution from hydropower and wind and also solar. So we're moving in the right direction, but there are still many challenges ahead of us to be able to grow this to be genuinely the dominant source of energy that we use in the world. And that's really where, you know, the RSM is positioning itself right now and looking forward into the future. The contribution we can make to driving uptake of these renewable energy sources. We no longer do any research now in fossil fuel exploration or production. Our focus is entirely on green energy and how we can grow that. So we're looking at technologies like geothermal energy and CO2 capture and storage, which you're going to hear a bit more about this evening. But also I could have talked about lots of other contributions the RSM is making to the energy transition through wind turbine optimization and ground engineering, tidal energy, energy storage in all its forms, including batteries, and also critical materials for the energy transition. We're not going to talk about that tonight. That's going to be the topic of a future evening lecture. And we've also really pivoted our educational offering to focus very much on green energy through our new master's courses. Now, I'm going to talk a bit about geothermal energy. That's kind of the part of this that I find it's all interesting, but the bit I particularly focus on. And you're also going to hear a bit more about geothermal from Jordan, who'll speak after me. So, geothermal. We know as we move at depth into the Earth, the temperature increases. In fact, the center of the Earth is incredibly hot, and there's a huge resource of energy there that we can tap. We never get that deep. We typically drill a few kilometers into the surface, the crust of the Earth. And when we do that, we find the temperature increases with depth. We call this the geotherm. And in fact, it varies quite a lot how steeply it changes. And that is controlled largely by geology. Okay, so plate tectonics, volcanic processes, the presence of magmatic bodies will influence how rapidly the temperature increases with depth. But we know the heat is down there and we can access it and use it. To do that, we essentially need three elements. Okay, we need to be able to drill some boreholes from the surface into the Earth to access the heat. We need to have some kind of fluid that we can pump through those boreholes. It's typically the groundwater that's naturally present in the rocks that we can inject into the hot rocks, pass them through the third element, which is some kind of heat exchanger. So the fluids can take the heat out of the rocks. We can pump those back to surface, and then we can use the energy to generate electricity or to provide heating. Now, in fact, there are many, many different types of geothermal technology. This is a schematic showing all of them, essentially showing different kind of rock layers and then different boreholes penetrating those with sort of showing the different kinds of geothermal technology that we can exploit. I would love to take you through all of these in detail in a 3 or 4 hour lecture, but I won't be able to do that. So I'm just going to focus on a couple of them. So when we think about geothermal energy, I think most people think about deep geothermal for electricity production. And they probably think about something that looks like this, where you've got kind of steam being produced maybe from a power plant in Iceland or New Zealand. And we typically do this at the moment in places where the rocks get hot, quite shallow. Okay, so this is Larderello in Italy. If we look at the temperature variation with depth, it gets really hot even as we reach a depth of a few kilometers. And in fact, we can produce steam at Larderello at 275 degrees Celsius. And in fact, Larderello is the world's oldest geothermal plant. It's not in New Zealand or in Iceland, it's in Italy. The Italians did it first. And typically, when we look for this kind of geothermal power, we're looking for these hot rocks to be quite close to the surface. If the water's too cool, we can still use it for heating. But generally speaking, as the temperature increases, we can start to generate electricity. And the higher the temperature of the fluids, the higher the temperature of the rocks, the more efficiently we can convert the geothermal energy into electricity. So that's great in a place like Larderello, where we can get hot at about 3 kilometers. In lots of other places in the world, at that depth, we're going to see much lower temperatures, which will be more suitable to provide heating, or we have to go a lot deeper to get to the kind of temperatures where electricity production becomes efficient. So one of the big research questions we're addressing here in the Royal School of Mines is, can we make geothermal electricity generation work anywhere? And to do that, we need to be able to get to those hot rocks at depth. We need to have cheap, fast drilling. We need to be able to get the heat out of those rocks really efficiently. And we need to make sure that when we drill those boreholes and engineer that heat exchange, it's going to work for a long time. And one of the other ideas we're looking at is whether we can use, in fact, create these deep hot reservoirs by using excess wind and solar energy when we can't use it elsewhere. So one of the big problems with renewables is they often generate too much at some times and not enough at other times. And we could capture and store that energy underground and bring it back to surface and use it to generate electricity when we need it. So these are just a few of the kind of research questions that we're looking to address as we move into the future. Now, a little UK focus. One of the ways that we can work out whether rocks are hot at depth is by looking at this, what's called the surface heat flux. So how much heat is passing through the surface of the Earth? And that's been mapped across the UK, in fact, largely across the world. And here that the areas of high heat flux, which indicate heat at depth, are shown by the hot colors in red, and the cold colors show us where there's not really very much heat present. So on my cover slide, I showed you a picture of United Downs, which is the UK's first commercial geothermal energy plant. If you were a geothermal explorationist looking to think where United Downs might be on this map, Where would you think it is? Yes, you see, you're really good at this. You've got the third one, 100% correct. Right down here in Cornwall, where we're now generating electricity for the first time in the UK from geothermal. Does that mean the rest of the UK is of no use to geothermal? Absolutely not. So in some ways, the kind of the unsung workhorse of geothermal is in fact low temperature, shallow geothermal, where we would target the upper few hundred meters of rocks and use the energy there to provide low carbon heating or cooling to the built environment. We could drill some boreholes, we can bring fluids to surface, and we can use those via a heat pump to provide heating or cooling, and sometimes even provide heating or cooling directly. And when I talk about this, this is essentially a large version of a ground source heat pump, but we're not really interested here in the kind of individual deployments that would supply a single house, residential property. We're interested here in big deployments that could supply lots of houses, an estate, or maybe a major university complex or a hospital via a heat network. So the kind of concept we're interested in here is that, a random grey block has appeared in the way, but we have a geothermal energy system that could provide a centralized energy center, which can then provide heating or cooling to the local built environment. And you will be connected to that energy network. We're very used to we're used to being connected to gas networks, electricity networks, water networks. We can also be connected to heat networks. And so rather than being given the gas to fire our boiler, we can be provided with the heat, and we choose how much of that we choose to take using a heat exchanger, a white box in your kitchen where you can turn a knob and change the temperature. And this would be the kind of scale that we're interested in deploying here, big geothermal projects that can supply these large energy networks. And the sorts of questions that we're looking to address here would be, this is a much more mature technology, certainly in the UK and Europe than deep geothermal. We already have around 55 or 60 geothermal projects in London, providing low carbon heating and cooling to buildings, and others elsewhere in the UK. In places like the Netherlands, they have thousands of installations like this. So it's a much more mature technology for us. So the kinds of research questions we're addressing here would be around how do we de-risk the way the aquifer behaves. You need to guarantee these systems are going to work, so you need to know how the aquifer is going to respond. Demonstrator projects that would help to build confidence in deploying these systems. How do we make sure that we make the maximum use of the rocks underground in somewhere like London, where it's a very dense urban environment with very high heating and cooling demand, fast tools for modeling these systems, and so on and so forth. And I think that this is a really big growth area. We've done some research to show that these kinds of technologies could provide around 60% of the UK's heating demand and about 80% of its current cooling demand if we rolled them out nationally. And that would allow us to provide a route to replace the 23 million gas boilers that we currently have in people's houses. And I think I'm going to stop there, but thank you very much. Oh, we're right in.
Can we put our hands together, please, for the fantastic Matt Jackson? Brilliant. And we have a question already from the audience. Alexander, I'm going to hand you this, if you can speak into it so everyone at home can hear.
Thank you very much, Alexander Follow-up, Eggshell. Question, you show a map of heat map, as you call it. Is that depending on the geology, the rock type, and what controls the heat?
Oh, so the surface flux that I showed, yes, that's very much dependent on the geology again. So those hot areas down here in Cornwall, they're associated with large granite intrusions, igneous intrusions, which are still hot, partly because they're cooling and partly because they're generating heat through radioactive decay. So yeah, very much controlled by the geology, the presence of deep basins and so forth, yeah.
Any other questions? Yeah, we've got another question in the middle of the room. Just for everyone at home, I'm going to carry on talking and filling the awkward silence whilst we walk through here.
So JJ Trainer, class of 85. Thanks very much for doing the presentation. Can I ask that a well was drilled in the Imperial Browns, I think, last summer. Could you comment on the results of that well and anything that we've learned from that?
They were. So the well was drilled to scope out the potential deployment of a closed loop geothermal system here at Imperial. So closed loop system is one where we pump fluids along the borehole but they remain within the borehole and exchange heat with the surrounding rocks. And it complements actually a borehole that was drilled just over 10 years ago in Prince's Gardens, which was designed to investigate whether an open loop system would work here at Imperial. So here the idea was that we have the chalk aquifer at about 80 meters underground. The chalk is a very productive aquifer. And the idea was to scope out whether an open loop system where we pump groundwater to surface would be suitable to heat and cool Imperial's campus. What the results showed was that, in fact, there's a lot of consistency between the two boreholes. We don't have lots of lateral variability. The chalk is present, quite heterogeneous. There's some very localized flow paths. So both open and closed loop systems would be feasible here. And right now, as far as I know, the decision is with the states as to which of those we proceed with, if either of them. Thank you.
Brilliant. I think we've got time for two more questions. So we're going to go for one more in the room, and then we've got a couple online, but we'll go for in the room first.
My name's Peter Dole, and I'm the class of 65, but not from here, from Southampton, just to give you my age. Oil and gas are indeed fossil fuels, but I'd invite the audience to remember that they're also the basis of the plastic industry, and almost everything in a hospital is plastic. And I just feel that giving it such a sort of negative connotation, oil and gas, is counterproductive, because there is so much in the material world that depends on those products.
I completely agree. But if you see here, the focus is very much on eliminating CO2 emissions through combustion of fossil fuels. And I think that is this is an absolutely pressing and urgent need for us to address. I think there's also a lot of interest in exploring alternative materials as well. They don't necessarily have to have a petrochemical origin. We've relied on them because we can produce them. But we also know that we have a serious microplastics issue and a nanoplastics issue now, that plastics have come with many benefits, but also with some significant downsides for the environment. So I'm not sure I personally see the ubiquitous use of plastics as necessarily a universal good, because I think we're now starting to see some very negative connotations from that use in the wider environment. So. We do, but that would be something that's very much the focus of our sister. So we're here in the Earth Science and Engineering Department. The Royal School of Mines also constitutes the Materials Department. And that's the kind of thing that they're very focused on investigating at the moment.
So for those of you who are online, that previous comment was around, yes, we need some substitution, for example, in there as well. Now, we've got two questions that have come in from online, Matt, and then I promise we will go to our next fantastic speaker. So the first is from David, and David asks, are the large energy companies investing in this technology?
In geothermal?
Yeah.
I think there's interest. And there is some engagement, but actually the sort of the geothermal industry did exist, before the hydrocarbon companies became interested in it. And there is already an existing geothermal industry that's very expert in these areas. So there is interest from that. There's clearly a lot of commonalities in the use of boreholes and pumping and understanding the subsurface. But I think we don't need to see the oil industry as a kind of a savior for geothermal. I think there is a good geothermal industry already there. It would be great to see some techniques coming through from the oil and gas industry that would support that. But an interest is welcome and expertise is welcome. But we do have quite a good geothermal industry already operating, and other entrants coming in who are disrupting that.
Brilliant. Thanks, Matt. And the final question is from Xi12. So I don't know if that is a class of something or it's a great tag name. And Zai's asking, how do we store this kind of energy?
How do we store it? That's a great question. Storage is one of the big challenges that we have. And as an underground person, I think the underground can also offer the solution, okay? So it's interesting that you comment on this. When I teach my master's students, one of the things we talk about is underground storage. We could store it thermal energy underground, and that could either be stored to buffer seasonal variations in renewable supply, or in fact, we can even capture waste heat from a building, store it underground in summer, and then reuse it in the winter to provide heating. And conversely, the same with cool energy. We can capture waste cool in the winter, store it underground as cool groundwater, and pump it back out to provide cooling in the summer. We actually have technologies already doing that. So there's one operating, for example, in Wandsworth. There's a poster about it there. So thank you very much, Si, for giving me the chance to point out there's a poster around this very technology. And we could also look at this at a larger scale to try and mitigate the intermittency of renewables. So I think the underground offers a huge reserve for storage. If you could change the temperature of the rock just under South Kensington, our campus, you took a 5-meter thick layer of rock and you change its temperature by 5 degrees, that already stores more energy than the world's biggest battery farm. The underground offers a huge potential for storage.
Who knew the secret ingredient here happens to be rocks? Excellent. So with that, everyone, please put your hands together for the fantastic Matt Jackson. So next up, we're going to go from Matt to one of our alumni. Now, Jordan Weddepohl is not only Chassen's flatmate from when you guys were studying here together. That we said, how would you like to be introduced? And he said, as Chass flatmate. Excellent. And I think your class of 2018?
Yeah.
Is that correct? And Jordan now works at Arup as a senior geologist. So put your hands together for Jordan. Thank you very much.
Yeah, brilliant. Yeah, it's great to be here. I work closely with Matt at the moment, but yeah, it's really nice to be back in G41. So quick one on who I am to people who don't know me. I graduated from Imperial in 2018 and joined Arup. Arup is an infrastructure consultancy from structural engineering to energy modeling to business advisory. Yeah, full spectrum of consultancy services. I kind of started geothermal consultancy 6 years ago in 2020. I've since been chartered and I actually won an award, the Glossop Award for the Early Career Geologist of the Year last year as a result of some of my geothermal levelized cost work. And I chair the Geothermal UK Business Case Working Group. So I'm heavily involved in the geothermal industry, trying to get it forward and progressed in the UK generally. And I've also been involved in a number of white papers that have been written in geothermal across the UK, presented at Parliament and a number of other conferences. It's a global role, and I've worked in projects across the world, 15 different countries. So moving on to the practicalities of, why do clients consider geothermal? It's a number of, it kind of varies on client and varies on location, but it comes down to a few things. Budget and return on investment is principal. Money talks. They want a system that is lowest cost for when they're replacing their older system, which is typically chillers and gas boilers. And geothermal offers a very competitive lifetime cost, but has quite a high upfront cost, which is sometimes prohibitive. Risk level, geothermal is relatively higher risk to say just a plug and play boiler, but it offers a greater kind of reward if the client is willing to kind of take that initial risk to develop a system program. So often clients have quite constrictive budget and decarbonisation targets, so maybe meeting a target by 2030, and geothermal can take a few more years to install just because of some funding and regulatory barriers. So it can just kind of fall by the wayside at that stage, and that's why we really want to get geothermal in the agenda, in the sphere, and people thinking about it early days, so it doesn't kind of not be considered just because of program constraints. We've also got energy demands. As Matt mentioned, geothermal is really suitable for high temperature and also large energy heating and cooling, or even power. So it's often looked at quite favorably in that respect because it can be scaled up quite well. Carbon, it's one of the lowest carbon heating and cooling solutions out there, and it's very favorable, especially if clients with more decarbonisation kind of targets in mind. And then maintenance. So geothermal can be a bit more onerous to maintain just because of interactions with different chemicals in the geothermal brines, so salinity. But there are all ways to mitigate around that, and you can just hire companies to kind of help clients that don't know how to manage these systems and kind of make sure that they're run effectively. And so what is required? So, it's a whole range, and you can hold the hand of the client throughout the whole process. It starts with feasibility. You do energy modeling, financial modeling, regulatory engagement, system design, then you hold their hand through commissioning and ongoing support throughout the process. So touching on some deep geothermal projects, Matt mentioned the highlights of shallow systems, but this is an example for a deep system, which is a bit more onerous, but there's just want to highlight the complexities of these things. So York University has recently been given 35 million in a government grant funding to develop a deep geothermal system at their campus. So step one is you need to do a feasibility model and understands the cost and the energy system and the estimates of what you're going to get out of that system. And these will inform regulatory discussions because you need regulatory approval to do these testing and drilling. And it'll also inform funding models because funding and getting it over that capital hurdle, which is quite high upfront costs, is often the biggest barrier to deep geothermal in the UK at the moment. Moving on to the next stage. So you've just secured funding. Brilliant. You're on your way to geothermal development. Procurement. There's a lot of contracts that are involved in deep geothermal drilling. You've got civil engineers, you've got plant designers, mechanical engineers, consultants, etc., drillers, etc. So you need to do all the procurement and make sure that all the contracts are in place and everyone's happy. A key one as well is the off-taker agreement. So for the funding to be allocated, you need to make sure that there's a suitable user of that heat or power. And that's often quite challenging because it's a chicken and egg. They want to see the resources there, but then they don't want to fund it until the offtake agreement is in place as well. And all of these, you also do some initial site surveying, so seismic surveys, just to refine those design assumptions and update your models. So then the exciting stage, so drilling your first well. This is everyone's really excited. It's taken a few years to get to this point. You've got all the rigs to the site and you're now ready to drill this well. So these wells, these rigs, they could be tens of tons and it takes 100 trucks to get it to site. They cost between 10 to 30,000 pounds per day to rent. And so as a result, time is money. You want to operate these systems continually for 24 hours a day from days to weeks to months, depending on how, what your well design is. And you want to make sure that everyone who can make those critical decisions is on site and available at a point's notice, so you don't waste time in decision making. So if something does go wrong and you need to, redesign the well, you can do so at that point. Once you've done the first well, you test it, you see what the flow rates are, the temperatures. If they fall within the suitable financial range, you can then progress with system design. If it unfortunately is relatively unproductive, normally due to a low flow rate, you may convert it to a single well system, it does work, it does generate heat, but it is to an order of magnitude less than what a doublet would do. And then the final stage is the plant construction, the commissioning and the operation. So these systems are typically designed for maybe 25-year life, but across the world, a lot of geothermal plants, heat or power, have been operating for more than 40 years. And we've got Southampton District Heating Network, Eden Geothermal, so the Eden biodomes, they're heated by geothermal sources, and United Downs was in the news recently for the UK's first geothermal power plant. So what's next in the UK? So, I've been doing this for 6 years and I've seen interest increase quite rapidly. We now have a geothermal minister, which is great. And geothermal is not just a footnote or a other category in geothermal policy documents. It's actually recognized and is increasingly being encouraged in energy strategies. National mapping, the British Geological Survey, Project Inner Space. There's a lot of national mapping work that's been done to show that geothermal resource is abundant from shallow to deep to power in Cornwall. It's just a use case of matching up the users and the demand. Cost models. I actually led the UK's first levelized cost modeling work for the UK government, and those models are readily being used for policy support, government and industry purposes at the moment. And then projects, I've highlighted a few projects, but there's far more geothermal in the UK than people probably realise, and hopefully in the next few years we'll see more and more coming up. There are a few barriers. A lot of these are not technical, so understanding and awareness, communication. Geothermal, as I said, can have a more extended program, and if it's not considered early doors, it might not just be discounted due to technicalities. So people might just think of geothermal as deep only for power. As Matt said, it can be used for shallow heat and cooling, used for energy storage. People just don't know. And and they may have inaccurate assumptions, which can straight away discount it at an early stage. So we're trying to raise the awareness, and hopefully you'll get the buzz and get excited about it and tell all your neighbors about it as well. But yeah, communication awareness is really a struggle at the moment, but it is getting better. We also have support mechanisms, government funding. So the government is actively funding a few select projects like University of York and some NHS hospitals, but there lacks a designated like standard funding mechanism. So that's grants or loans or risk mitigation mechanisms. And it's kind of a chicken and egg between private funding stepping in and government funding. But if government really stepped forward, it would show that they're backing geothermal, which would increase private investor confidence, and it would kind of snowball effect and bring in a lot more investment. So the opportunities, as kind of Matt said, drilling costs it's expensive to drill, and often it's a capital hurdle. So if you can reduce drilling costs, especially deep drilling, it will massively revolutionize the kind of the geothermal market and the economics around geothermal development. In the US, Project Forge, which is a US Energy Department government-funded exercise, it's a $500 million research vessel in Utah, and then Fervo, which is a commercial spin-off from that. In 10 years, they have seen 5-fold increases in drilling rate, 300% drilling well outputs, and as a result, they've halved their levelized costs. So, UK has very competent drilling expertise, some of the best drillers in the world. If we can realize these costs, the economics of geothermal will be far more favorable, and we'll see it rolled out across the UK. We're also doing the heat network zoning work at the moment. So that's 28 cities across the UK are being studied in detail using district heating networks. So connecting heat supplies like geothermal to heat users like industry and residents. And geothermal is part of that story. And Matt and I, we're trying to get in the mix and encourage UTES, underground thermal energy storage, deep geothermal heating and cooling, to really be a core consideration as part of that narrative. And it is increasingly becoming more interested by, government is getting more interested by it because the costs are looking quite strong. NHS, we've got 8 NHS hospitals currently been looking at geothermal. And lithium. So there are other elements of geothermal which are, a benefit. So the United Downs project in Cornwall had found elevated levels of lithium in their brine that was produced, 400 parts per million. Now, lithium brine, lithium chlorides, can be converted into lithium hydroxide or lithium carbonate products, which is a precursor to battery generation. Batteries and lithium is a prime commodity, and the sale price at the moment ranges between $30,000 to $80,000 US. And if lithium works at scale, it actually far outpaces the revenue you get from geothermal power and heat anyway. So yeah, if lithium comes up in anger, it's going to be quite exciting in the UK. So hopefully you can see that the UK has seen a geothermal uptick, and it is positive moving forward. But yeah, it's been Jordan Weddepohl. It's been a pleasure to talk, and just get in touch. Always happy to discuss geothermal.
Fantastic. Please put your hands together for the fantastic Jordan.
Right. Have you got any questions for Jordan in the room initially? No, I can go to one online, which didn't get asked before. So actually, you finished on talking about lithium. So there's actually one that was asked to Matt initially. So it's from Eduardo Gomez, who's online. He said, I understand the Cornwall project has the added benefit of being able to extract lithium brine as well as heat.
Yep. What
are your thoughts on this technology? And are there reliable ways of mapping the duality of lithium and heat sources?
Well, it's come up quite favorably in Cornwall, but also in County Durham and Weardale. So it's kind of linked to granite sources. And then granites have, as Matt was saying, radiogenic decay, higher heat flows. So there's kind of a pairing naturally. The geothermal, the lithium resource depends on the concentration they get. So in Weardale, they had, I think, 140 parts per million. Cornwall, they got 400 parts per million. There's questions about, is that resource finite? How large is that resource? It's difficult to quantify. There's also mechanical processing barriers. It is a rate-dependent bottlenecking. So, you can only store and process so much lithium brine at surface, even though you're continually producing geothermal brine. So they need to scale up their facilities. So they're moving from pilot scale, which is kind of hundreds of tons, to semi-commercial, which is thousands of tons, to commercial, which is tens of thousands of tons. But there are much larger projects. So Project Vulcan in Germany, they've invested, I think, it's hundreds of billions. And as part of my levelized cost work I did, like the revenue of that is crazy high if it works. So yeah, it's exciting times. But then you're also at the risk of external markets. So if China just floods the market with cheaper lithium, then your quantity price comes down. So yeah, there's a lot of factors to consider.
Thanks. Any questions in the room?
Hey, Jordan. I was going to ask about the operational side of things. The geothermal wells, are they drilled using the same technology as oil and gas wells?
You kind of, yeah, it's a productive reservoir, but you would avoid oil and gas horizons just because of co-producing. So it's more saline water sources, and then as you operate it, you just monitor the temperature, the flow rates, the pressures, and over time, you'll see these dropping. So, and if you don't manage the pressures effectively, you might need to clean them out or do some workover rigs on those wells, or you may need to drill some top-up wells just to top up that supply. So places like Turkey, they have less of a, they're more of a reactive maintenance schedule where they just work the wells really hard and then just maybe do a bit of top-up when they can. But in other countries like the US, they have a bit more proactive maintenance scheme where they will have a regular workover rigs to kind of make sure the wells are operating and not scaling up and not fouling up. But yeah.
Thank you.
Go. Oh, yeah.
Jordan, thanks for your talk.
Good to see you.
What do you think are the biggest policy changes that actually might make a difference in terms of expanding geothermal? What do you think the government could or should be doing, or do you think actually this should be private sector led?
Yeah, so as I say, it's a bit of a chicken and egg between government and private, because the government says that if it's such a good investment, why does private sector do it? And if the private sector, they're unwilling to invest because they're saying, well, what if a policy comes in place which then undercuts their investment? So yeah, it's a chicken and egg, but we are increasingly getting interest from the big DNOs, the district network operators, and the ESCOs, the energy system operators, who are looking at these district heating networks. Regarding actual policies, there are risk sharing measures for drilling. So, you invest in one well or a portfolio of wells. If one well underperforms or performs well, it kind of funds the next well. And these kind of measures have been implemented really effectively in Netherlands, Germany, and France. There's also official grants, but they don't end up with a remuneration for the government, so they're less favoured. Or it's just standard loans where the government does get a stipend at the end of it, or a tariff at the end of it, if the well is successful. So there's a number of different ways the government could support it, but as I say, it's a challenging market at the moment. But yeah, a lot of these discussions with policymakers is you say the same thing over and over again.
Okay. All right. I think we'll leave it there and go on to the next speaker. Can we just thank Jordan again, please?
Brilliant. So last but by no means least this evening, if we can welcome to the stage Nihal, who, what was it, in the last month you received the certificate for your PhD, which I think is pretty phenomenal. So please give her a round of applause just for that. Nihal Darraj is now a research associate in carbon dioxide removal and is going to give us some insights into carbon capture and storage. Thank you very much.
Hi, everyone. So I'm no one's roommate. My name is Nihal Darraj. I got my first degree with my background is in engineering. I got it 15 years ago. And then I went and worked for a company in Texas called Advantech International, looking at oil and gas waste. So reinjection of produced water and drill cuttings and sometimes CO2 storage. And then after that, I decided to come back to school and get my postgraduate degrees. So I did both my master's and my PhD at the department. And as Sarah said, I just finished my PhD, I think a month ago. So I could bore you to death with macroscopic and pore scale processes for CO2 storage and continuum scale, but to bridge what I've done in my PhD with what I'm doing in my postdoc, I decided to go a little bit with big picture. All right. So do we know that we emit 40 gigaton of CO2 per year? First of all, what's a gigaton? Okay, so if you're in tune with what's happening in the Middle East, a gigaton, 1 gigaton, is basically the weight of 10,000 fully loaded US aircraft carriers. If you're not in tune with what's happening in the Middle East, it's basically the weight of 100 million African elephants. All right, so all of these emissions, we need to store them somewhere. We need to reduce them. Today, I decided to talk about hard-to-abate sectors. What are hard-to-abate sectors? They are the sectors where if you use renewables, geothermal, electrification, all these great technologies, they still have CO2 emissions. So these sectors emit around 9 gigaton of CO2 per year. The IEA, in their 2023 report, they said that we need to store at least by 2050 6 gigaton of these hard-to-abate sectors emissions. And the reason I chose this is that, as I said, this would answer the question of CCS is a way to prolong oil and gas. Well, actually, for these industries, it might be the only solution for them to go to net zero. Okay, so what is CO2 storage? CO2 storage is basically the entire value chain is capture, and then condition and transport, and then store. So to be able to store CO2, you need to put it in something called a supercritical condition, which is a super cool condition, basically. It's as dense as liquid, so when you store it, it sort of falls down and not float in the reservoir, and with the viscosity of a gas to be able to actually pump it into the reservoir. The way we store CO2, and this is where we answer the second question I'm about to ask, will CO2 leak? So to be able to store it, you need to store it in a depth of above 800 meters. The reason being because you need to keep the CO2 in a supercritical condition. Why do we need to keep it in a supercritical condition? As you see, if it's a gas, it will take a large space. If it's a liquid, it will take a smaller space, so it will maximize your storage capacity. This CO2 that you store can be in a porous rock, similar to the oil and gas industry, basically, which is we can store it in saline aquifer, you can store it in sandstone or carbonate or whatnot. There are other places that you can store CO2, which is in a basalt formation. There's a project called CarbFix in Iceland, where you basically inject water charged with CO2 and the CO2 mineralizes. So these formations are formations that are rich in calcium and magnesium, and the CO2 reacts with calcium and magnesium and produce salts. So magnesium carbonate and calcium carbonate, and this is a form of permanent storage. With the storage in depleted oil and gas fields and saline aquifer, which is basically the conventional CO2 storage, you will have to have a impermeable rock or a seal to keep your CO2 underground, which is basically similar to the gas reservoirs that we all know from oil and gas. Okay, so if you read the report or looked at the report, the IPCC report about the trapping mechanisms in CO2, you would find that CO2 would be basically trapped in the reservoir by multiple mechanisms. Structural trapping, residual trapping, solubility trapping, and mineral trapping. Structural trapping is when your CO2 basically goes right under your impermeable rock. The other one is residual trapping, which when basically your CO2 moves through the reservoir, your water re-imbibe into the reservoir, it snap off the CO2 into bubbles that are stored in the reservoir. And then solubility trapping is where your CO2 is basically traveling through the reservoir and it dissolves in the formation brine as it goes. Last one is mineral trapping, which is basically reaction with the carbonates and minerals in the reservoir. So it forms a salt and it's permanently stored in the reservoir. So see, residual trapping is when you have a snap off, but there is another way of capillary trapping is when you have a geological heterogeneity. So if you work in oil and gas reservoirs or like oil and gas industry in general, heterogeneity is not your friend. But if you're in CO2 storage, heterogeneity is your friend because it will trap more CO2. There's a very cool concept called composite confining, which was published by Alex Pump in UT Austin. It's a very nice paper if you want to read it. We do this type of research here at Imperial. In fact, my PhD was on trapping by capillary heterogeneity. So as we said, the more the CO2 is in your reservoir, the more it stays there, the more the storage security increases with time. Are we saying it will never leak? No, we're not saying this, but we're saying that your security basically increases with time. Okay, so here I sort of tried to look at this from a point of view that I'm not working basically in the CCS industry. So here's the annual leakage or seepage rate per stored volume in natural gas reservoirs. And here's in nuclear waste and dam seepage and hydropower. And then here is in your LNG store tank, and here is your geological storage. So the risk of leakage is actually quite small. With the IPCC report, the containment probability for CCS is actually 98.9%, which is very close to the nuclear waste. So that tells you that storing CO2 in the subsurface is actually safe. And the best part about it is we know how to do it. So the safety factor basically is 10 times better than the IPCC target of 99% of the total CO2 stored. Does anyone know the safety factor of aviation or like basically getting on a plane? It's 2. The CO2 storage is 10. All right, so if it's that cool, if it's that great, why it's not very widely deployed? Well, we're trying. So if you look here, this is what the IEA projected that we will have in 2050. And here we are. This is what is actually happening. So to get from here to here, we have a long way to go. The challenges are not just technical. There are regulatory, there are political, there are economic. So for example, Norway, we've seen that the Northern Lights project, if you heard about it, it was heavily subsidized by the government. So that's one way that we've seen CCS projects actually happening and succeeding. Other problems is that the location of the storage or like the field that you store in. So basically some countries would have the CO2 to store, but they won't have any storage capacity, or they have regulation in place that prevent them from storing, for example, Finland. Other countries would have the store, but not the CO2, so you will need to import the the CO2 from somewhere else, and this will get you to something else called the London Protocol of moving waste across border. So yeah, there are a lot of hurdles that we need to basically get over to move from here to here. And with that, I've done my talk. Thank you so much.
Brilliant. Thanks so much, Nihal. Have we got any questions in the room? Go for it.
Yeah, you mentioned the leakage rate or whatever. Do you have data to verify that?
Yes. So if you look at Sleipner in Norway, it's a project that has been going on since the 90s. They successfully stored around 22 million million tons of CO2, and they haven't had any leakage. There are other projects, so you can look at these projects. Also, Snøhvit in Norway as well. And let me sort of make a distinction here. So if the CO2 moves or like migrated within the storage complex, it's called migration, even if it's moved from one layer to the other. But we only say leaks if it goes all the way up to the surface. So yeah, because you'll hear people like saying it leaked. It did not leak. It just moved basically or migrated from one formation to the other.
Got a question online quickly. So Davide online was wondering, how is the seepage factor from geological storage measured?
So basically, you measure how much you stored. Sometimes with these leakage parameters, you can actually the monitoring, MMV. So you can you measure something called baseline CO2, and then you measure again, and you see the difference between the two, and you know how much basically you store. So this becomes a mass balance issue. There's another technique that is called I'm sorry, I'm not a geologist, but it's like full wave something length. Yeah, exactly. So in NTNU, they were able to basically look at the is that my phone? Sorry. So they were able to look at the plume and calculate how much they have in the reservoir and back calculate what they actually stored. And it was almost the same. So they calculated the thing that they stored 19.6 million tons, and they actually stored 9.1. So there is, of course, an error, but it's basically all stayed there. So yeah.
Questions in the room?
Was it that good or that bad?
Oh, here we go. Here we go.
Hi, thanks for the talk. So you showed a plot on the last slide, which said we want to increase the amount of yearly CO2 stored by a factor of 100 in about 25 years.
The number of projects. So these were the actual projects, and then yeah, this is what we're storing now, and this is what we need to store. So apparently there's a need for speed.
So it's about a 20% year-on-year growth. How does that compare to the historical trend?
Oh, okay. So I think Sam Carver is the best one to answer this question. So CO2 has been historically stored through EUR, and we've successfully stored 1 gigaton of CO2 underground from CO2 EUR. Technologically speaking, so the growth rate of technology is around 10% a year. So this target is completely unrealistic.
Thanks. It's good to get your opinion on it.
Sarah, did you want to?
So I think what we're going to do now is we're going to welcome all of our speakers up to the stage. But firstly, please give Nihal a fantastic round of applause. Okay, so while our speakers move up to the stage, one of the things that Fred and I found really interesting in terms of putting together these lecture events is when you say something like energy transition or geohazards or raw materials, it means very different things to different people. So I'm sure here in the room, some of you are sitting here going, oh, what about this? What about that? And one of the things that we're doing over the course of this year is putting together a podcast. So we'd love to hear your thoughts about the different areas of research, learning, development, innovation that we've seen not only over the last 175 years, but also where are we going over the next 175 years. So if you've got comments you'd like to make, if you feel that there are aspects of the energy transition that we haven't talked about this evening, please come and find me afterwards, as I will have a microphone in my hand. You don't have to speak into it, don't worry. But if there is something you'd like to add, please do say. We've also got different aspects of the energy transition that we'll be discussing later on in the year. So, for example, Matt mentioned things like critical minerals in passing. Well, we've got a whole evening that's dedicated to raw materials, some of which may be critical, for example. And then later on in the year, we've got our very own head of department, Tina, whose background is very much in the world of climate change, etc. So I know that we've booked you, Tina, haven't we, to be able to speak a little bit about those aspects as well. Because if nothing else in the world of earth science and engineering, everything that we're studying is really interconnected and very much helps one another, not only to develop, but sometimes impinges on one another as well. So coming into our panel session here, and I know that between Fred and myself, we're going to attempt to juggle what's going on online as well as what's going on in the room. If any of you have any questions, please do feel free to pose them. But just to start with, and I'm going to come to Jordan first. So Jordan, were you taught by Matt?
I don't think so. I think I did more of the geology rather than geophysics. I think you did a lot of the more numerical stuff that went way over my head. So no.
Well, that's good. So we can't embarrass you too badly. But in terms of thinking back to your time within the department, are there any key memories that you either want to share, or do we need to come and ask you during the network afterwards? What was it like being a student here within the department?
Yeah, I mean, my favorite was just all the field trips. I mean, every year we did 2-3 field trips. It was brilliant. Always on my birthday as well. So had a great time. Maybe too much of a good time sometimes, but we won't get to that. Yeah, no, it was brilliant. And the people, I like the size of the department. You know, it's 30 people in the MSci course, so you got to know everyone really, really intimately, and it was, you know, everyone had a really good friendship and camaraderie and help each other out, and everyone's doing really well for themselves now, so it's great.
Fantastic, thank you. And Nihal, how about yourself? What was it like studying for your PhD, etc., here in the department?
Well, it was great. See, I came to Imperial with 10 years of experience, so I was like the dinosaur in the room always. So I sort of felt a little bit taken back, but I remember all my professor Matt, he was my tutor, and Martin Blunt was my supervisor during my master's, and Sam Crever as well. And they sort of walked me through how to take notes again and attend lectures and, you know, go to the trenches. Literally, my lab is in the basement, and, you know, do research. So yeah, I'm very grateful. I could literally hear Sam's voice when I was doing the presentation, like do this, do that. So yeah, he didn't do anything in it, but, you know, it resonates with you. It's you know, coming here with a long experience, you would think that you won't learn a lot, but it completely changed me. So yeah.
Brilliant. And Matt, you've been here for a little while. Are there any comments that you want to share with the room in terms of either how the department has changed, or any key memories you'd like to share? Maybe if you take Nihal's microphone.
I think the department has changed a lot. I have been here a long time, longer than I care to admit. And it is interesting that the energy transition is probably one of those major changes that has massively influenced what we do here in terms of research and in terms of teaching. And I think I'm actually really, I mean, one of the things I'm proud of is the way the department has managed that transition. To go from having some really major teaching programs that were very focused on oil and gas, and to have been able to translate our expertise into, you know, educating students around renewable energy technologies, while still maintaining, you know, the focus on really good field trips and so forth. And to see how the department has evolved in that way in a very at a very fast pace. You know, the big departments are like oil tankers. You know, they normally take a very long time to turn around, and we've managed to turn this one pretty quickly, actually, and in a very successful way.
Okay, maybe let's open it up to the floor now. Have you got any questions that you wanted to ask about anything related to the energy transition?
Just while Fred is taking the microphone halfway down the room, this is going to be the dance of the microphones this evening. But those of you who are online, please do keep your comments coming. There's been a really good discussion around the concentration of lithium coming out the ground of certain holes, etc. So Jordan, you'll have a lovely time addressing some of those comments later. But yeah, over to the question in the room.
Yeah, hi, I'm Idris, current PhD student in the department. This is for Jordan and Matt. Thanks for the presentation. Great presentations all through. I think, Jordan, you did mention the Utah Forge and some further projects, but I think I'm aware that those involve some sort of fracturing of the rock. Can we expect some of that in the UK in the near future, or is this more sort of naturally fractured and sort of more hydrothermal systems?
Yeah, no, really good point. So deep geothermal's kind of got two end members, well, three. We got the reservoir dependent, so hydrothermal. You need active porosity, permeability in the rocks. Then you've got reservoir independent, which is granites, and you hydraulically stimulate the rocks, generate your artificial. These are dry rocks. You stimulate them, generate an artificial reservoir, and flow fluids between that. And that's what they've been doing in Utah Forge. What they did in Cornwall was similar to kind of a blend of two. They targeted a natural fracture, but there was some kind of stimulation there as well. What they've achieved in the US and Utah Forge and Fervo, I think Fervo's got its IPO coming out soon as well, which is exciting. They're revolutionizing geothermal independent power generation, and it's really caught the attention of data centers and with the recent AI boom, because you can generate power almost anywhere, really. You just need the right heat source. So yeah, it's exciting. You've also got the other, it's called advanced geothermal systems, where they basically generate a radiator underground. So they drill one well this way, one well this way, connect the two in between, and flow fluids between. So yeah, we'll see how that develops in the future.
Great. No, I think all I'd add there is that, in Cornwall with the United Downs, there were some fractures created in the granite as they were sort of bringing the system on stream. And that did in fact lead to some felt vibrations at the surface. And I think what United Downs did very, very successfully was to have an incredibly strong outreach. And they really engaged a lot with the local community to explain that this could happen, to explain why it was happening, and to show them that there was a bigger picture benefit to doing this. And I think if you can, these projects where these fractures are created underground, they will always have some risk of that. But if you're really open about what you're doing, if you're really engaged with the community, I think the community can be much more accepting of it. I think it's when companies go in there with a very closed attitude, they try and keep the local community at arm's length. They don't explain what they're doing. That's when communities start to feel hostile towards what's happening, and when there starts to be a negative view of what the company's doing. So, it was experienced, but it was not negatively viewed by the local community.
Any other question in the room, or comment or feedback?
If not, I can go to some. So there were some questions online that we got around to. So one thing that was asked online, and maybe this is again kind of more geothermal focused, but maybe we could also open up to Nihal as well in terms of the kind of CCS. So the thing about this is a department that educates the geoscientists of the future, the engineering geoscientists of the future. What do you think that kind of are the main skills we actually need to be teaching our undergrads, our postgrads, our PhD students to kind of make geothermal happen in the UK, or to expand kind of the uptake of CCS?
Okay, that's a great question, and I think for me, it's not around a specific set of skills. It's around having a very open mind to work across different disciplines and to listen to different disciplines to understand what they're trying to do and to be able to integrate that in the way that you view a problem. And it's actually something that builds on quite a long tradition of how we've tried to educate our students here in the department. And I was actually having a conversation about this over lunch earlier today. You know, all of these kinds of technologies, they require a really close integration between people who understand geology and people who understand the engineering. And if those two disciplines can really communicate with each other effectively, then you're far more likely to see success in the deployment of these technologies. If those two disciplines become very siloed and very isolated from each other, then it's far more likely that something will go wrong because people aren't really understanding the problem they're dealing with. And actually, one of the things I really like about this department is that we are a department of earth science and engineering, one of the few places in the world where we bring those two disciplines under the same roof and so they can really interact with each other. So that for me is probably one of the really important things we need to continue teaching our students, you know, as we go into the future, as we continue to engineer, hopefully ever more effectively, these new technologies for the energy transition.
Yeah, so actually, Matt brings a very good point. I did Masters of Petroleum Engineering here, and one of the main things that we used to do is basically a field development plan where we used to communicate with our fellow geoscientists to actually get the point across. So that's actually a very good point because we don't speak the same language. With geoscience, more of an art. With us engineers, we need numbers. It's like, what do you mean? It could be this. It needs to be 0 or 1, you know? So for me, as I said, I did a Master's of Petroleum Engineering, and then I did core analysis for CO2 storage. So the science is the same. It's a different fluid. So once we lay down these bases and keep an open mind of what you can actually do, then you'd be able to do anything. If you're gonna work in storage, if someone's going to be working in storage, and you can ask anyone if they're working, let's say, for BP. Today, the person is in the CCS team. Tomorrow, they're doing exploration. And then maybe move to the geothermal. So keeping an open mind and learning these skills is the key, in my opinion.
Final thing to add is the benefit of geothermal is there's such a range of disciplines that get involved. So it's not just the nitty gritty, the specialist geologists and you know, geothermal engineers. You also have the environmental engineers doing the regulatory side. You have economics and finance specialists across the whole thing, because these things do need a lot of financial decision making. Civil engineers building pad foundation, mechanical engineers doing the plant design, district heating networks, energy specialists working out the heating cooling profiles, the power generation loads. So it's great. I mean, if the industry grows, there's a wealth of opportunity, not just for people coming out of the courses that Imperial present, but you know, the whole of Imperial and non-engineering disciplines.
Yeah, I love that. Engineers and geoscientists not being able to communicate, let alone everybody else.
We've got a question in the room. Go on, have you other?
I know we've got another question that's come in online, but we'll go to the room first and then online.
So maybe a bit too philosophical, but the term energy transition, has the panel thought about energy transitions in the past and what caused those transitions to happen? Is there anything from those lessons that we can learn and look at with respect to what's happening today?
So you're absolutely right. We've been through several energy transitions. You know, we went through one. I very briefly alluded to it when we went into the coal age. We actually moved away from an age where we were already using far more renewable energy. So we were using wind power in windmills. We were using water power. We were using horsepower. We were burning wood, but it was largely wood that was being grown, and so it was replenished wood. And we moved into the coal age, and that was largely driven, I think, by demand. Okay, there was this huge demand for energy to power the Industrial Revolution, and burning coal was the best way to get at that. And so we had this huge explosion. We then went through a number of other transitions. So we actually went through, I mean, we kind of talk about replacing gas boilers in the UK, but we did also we went through a great change from, say, town gas to to natural gas, but natural gas became a resource that was far more widely available, and everybody had their, their gas burners replaced because they had to be engineered differently for natural gas. And we kind of went through that, and we moved away from burning coal in fireplaces, because it was causing huge amounts of pollution in cities, like London, where we had smog. So there was a lot of push there that moving to that was seen as being beneficial. Okay, I did a lot of work to find out whether there were people opposing the transition from coal to smokeless fuel and to gas, and actually it was being pushed by the community because they could see it was going to be beneficial for health overall. So I think sometimes these transitions are driven by the urgent need for a big expansion in energy, which maybe drove the coal uptake. But sometimes they're pushed by the community because they can see the benefits of the replacement energy source. And I think that's partly where we are now with the energy transition. So there are some pushes by government, and there are some pushes that are coming economically and through geopolitical stability and so forth, where we can see the advantages of transitioning to renewable energy. But I think an awful lot of it's coming from the community, who can see the overall benefits of a transition, in the sense that they are concerned about the state of the environment that will be left, as we move into later generations, and wanting to be responsible about how we hand on the inheritance to our successors. So I think there's a push there that's pushing us towards the move to renewables, as well as a pull that's taking us away from using an energy source which is becoming increasingly unstable in the current geopolitical climate.
I mean, just perhaps to add to that, politicians, I think we all know, a pretty short-term bunch. Getting them to focus more on issues around air quality rather than sort of 15, 20-year energy transition themes, that might be much more effective, actually, in terms of lobbying politicians. So the pollution in this city that's coming from diesel, for example.
I agree completely. We can see other spin-off benefits from, say, electrification of vehicles, moving away from other harmful emissions. Combustion produces a lot of harmful things. It's not just CO2, you're completely right. Even combustion in the home, around burning about gas hobs and so forth, actually produces a surprising number of really unpleasant chemicals. And so to move away from that, to me, in the very broadest sense, feels like a very progressive move. And I can't help but think that, in 170 years' time, 175 years' time, when we're looking at hopefully celebrating the next centenary of the Royal School of Mines, we will look back on this as the age of combustion, and as really quite a primitive age.
So I have one more comment, actually. I agree with everything Matt said, but I feel like it's also related to the image of the oil and gas industry in the place. So if you look at the Middle East, for example, what did the oil and gas industry did for the Middle East? It built communities, it basically built the entire country, right? But if you look at North America, where the oil and gas companies basically destroyed everything, then you will have a very negative image of the industry there. So I think that's also a big push.
One final thing, sorry. Electricity is easily transmitted, but heat is place-based, and it's far more difficult to transfer across long distances. So I think there's a transition to better use your heat resource at its local point, and also benefit grid stabilization, underground thermal energy storage, and things that come with it.
So we've had one final but quite beefy question that's come in online.
So yeah, this is actually from Mike Mayo. He says, to ask a big question, which it is, the problem seems to me that there's no real creditable plan for the energy transition in the UK, let alone the world. The talks had tonight are all great ideas, but all fraught with issues, i.e. they are possibilities, not real options. I guess that could be something we can debate. Would it be an idea for the department to clearly demonstrate how these possibilities really fit into the bigger picture of energy transition?
I'll have a start. We are involved in a lot of these larger scale, governmental thinking and investment discussions. I work with Matt on some of these things, and so the department is actively supporting it. Decision making is slow, especially when you're considering on a national scale. And we are more risk averse in the UK than, say, our neighbours in the US, where they kind of throw money at it, see if it works. If it works, great. If it doesn't, we'll go again. in the UK, there's a bit more hesitation. But I hope that through some more projects, case study successes, we should see a shift in that. And we have a industry primed and really excited and raring to go to kind of back that horse.
I guess coming from perhaps a more geothermal perspective, and perhaps we could hear your view on the CO2 storage angle, but I think I'd probably quietly take issue with the idea that what we've heard today are only ideas and not technologies that are already being deployed today. Jordan and I could both take you to places in London right now where buildings are being heated and cooled by renewable geothermal energy. Okay, there are proven examples out there. As I said, there are around 55, 60 deployments already just in London. What's the problem now is not so much around the basic technology understanding, it's around the really widespread uptake of these technologies. And Jordan mentioned that, one of the barriers we have to this is really just around awareness that these are technology options that are available. So I think we've come past that first stage, which is just ideas. Now we're taking things which have been provably demonstrated and we're just trying to really scale them up to have very widespread uptake. And that does then require us to displace the incumbent, which is gas. And that's going to be challenging. Okay, we have, as I said, 23 million gas boilers in the UK. And I think going back to the earlier question we had as well, what do we learn from transitions? They're always going to be painful because you are going to have to do work to take out the incumbent technology and to replace it with something which is ultimately going to be better. And there will naturally be, in many cases, resistance to that. People don't want people coming into their homes, telling them they can't have their gas boilers or their gas cookers and so forth. And so there is a greater good. And I think we just have to really keep working to reach out, to work with people to understand why these transitions are necessary and to encourage the take-up of these new options, not just by individuals, but also by institutions, large corporations and so forth, who can lead the way in putting these systems in and getting them used by the general public.
Well, I mean, for CCS is different because the technology is already proven. The government is already investing in it. I think the only thing is that it takes a very long time, as Jordan said, to permit to do the permitting work. The other thing is basically financing the project itself. So do I drill a new well? Do I use the existing well? And all of these decisions can take a long time. But other than that, I feel like it's on track.
So nice, optimistic set of answers there, which is brilliant. So final question to all three of you, which is, okay, so we've got 175 years of history. The Department for Earth Science and Engineering, we've been around for 25 years. If we look forwards to the next 25 years, so making this a little bit more achievable than perhaps the next 175, but the next 25 years, what do you hope we will see? Do you anticipate any transitions, for example, that we might see over the next 25 years with regards to the world of energy?
Okay, I don't have a very specific answer to this, but whatever the world is heading to, every stream of energy, I would like to see imperial people working in it. So
I really do hope that in 25 years' time, we'll be sitting in a room which is heated and cooled by a renewable source, and that we are in the majority in a big city like London rather than the minority. And I think that given the rate of increase in the deployment of renewables in the UK, that's not an unrealistic target. So it'd be to reach that point where now renewables is the majority option rather than the minority option. That would be my hope for the next 25 years.
I think that district heating networks will be well known and utilized. Thermal storage will be far more commonplace, especially underground thermal energy storage. And I think in the more power suitable geothermal areas, we'll see much larger scale deployment in places like the US.
Brilliant. So with that, please put your hands together for our fantastic panel. So that concludes this evening's events, as in the formal ones that are here and being transmitted to those of you at home dialing in on Teams. The rest of us here, not only are we trapped in the department, you didn't know that, did you? No, we're trapped here in the department because, of course, there is a tube strike. So, well, we've got nowhere else to be. Apparently, the doors don't lock until 11:59. Is that right, Tina? So catering has left a variety of drinks and food next door. We've also got some posters here on the walls. But before you do go, this is our first of a number of different events. Please give us your feedback, because we know that we can improve them. We know that we can make them much more useful. But also there are some key people in this room who also need another round of applause. The likes of Gege, our fantastic volunteers who have put all of this together. Can you give them a round of applause, please? We also have some thank you gifts. So they are branded water bottles. Oh, yes. For our speakers. Anybody here who would like branded swag, come and see us, because if that's something you would like, we can make sure it is much more available for future lecture series that we have. As previously mentioned, our next lecture is on the topic of geohazards. So we have a variety of different aspects of that topic that we'll be exploring. That's in May. And then in June, we're going to be talking about raw materials, and these lectures will continue on throughout the rest of the year. So with that, thank you very, very much, everybody, for coming. I will pass over to Fred for any final words of wisdom.
Not really, actually. Just thank you, guys, and please enjoy the refreshments.